Hi everyone, and thank you for joining my talk on structured entangled photons. Since the seminal works of the Zeilinger group over 2 decades ago, people have realized that there are lots of advantages of structuring single and entangled photons. For example, when you encode bits of information in the structure of photons, you can encode much more than a single bit in a single photon. It's also been shown that quantum communication protocols that are based on structured photons can show high resilience to noise, and they can also show stronger violations of Bell inequalities. So here's an example of entangled artistic view of entangled photons where they are entangled in the structure. And this was taken by this nice review, recent review by Forbes et al. Nature Photonics. Now, what I want to tell you about today is about adaptive structuring and adaptive shaping of entangled photons. And the motivation for this work is that in recent years, we've seen more and more examples where people are using quantum states of light in real life scenarios. So here's one fantastic example you may have heard of, that the Chinese Academy of Science have launched a satellite about 4 years ago that is now orbiting around Earth. And as it orbits around Earth, it sends pairs of entangled photons to ground stations on Earth. Now, these photons have to pass through the atmosphere, and this atmosphere can be turbulent and it can scatter the photons. And if you really want to use the full capacity of entangled photons as they pass through aberrations and scattering, we must be able to adaptively control their shape so that they will be properly detected on Earth. So this is the motivation for the work. But let me start, before getting into the details of what we've done, let me now more properly explain what do we mean by spatially entangled photons, and I'll do this by explaining how we generate them in the lab. So the process we use for generating pairs of entangled photons in the lab is called spontaneous parametric down conversion, where we take a strong bright laser beam, a blue laser in our case, and focus it on a nonlinear crystal. Now, due to the nonlinear interactions in the crystal, every now and then a pump photon can split into two lower energy photons called signal and idler photons. And this process has to conserve energy. So the sum of the frequencies of the signal and idler photons must add up to be equal to the frequency of the pump photon. And most of our work is in the degenerate case where we set the frequencies to be equal. But it also needs to conserve momentum, which means that the sum of the wave vectors of the signal and idler photons must be equal to the wave vector of the pump photon. In the nonlinear optics ergon, this is also called the phase matching condition. Now, because of the phase matching condition or the momentum conservation, we could tweak the crystal parameters such that the photons will be emitted in a wide range of angles. So we don't know at which angle the signal and idler photons are emitted. But because of momentum conservation, we know that they will always be emitted in anti-correlated angles. Okay, so if the signal is emitted in a plus delta angle, the idler will be emitted in a minus delta angle. And we can write the quantum state of the photon pairs that are emitted from this crystal as a superposition of states, where in each state the signal photon has some transverse momentum and the idler photon has exactly the opposite transverse momentum. And the number of states in this superposition is called the Schmidt rank, and as long as it's larger than 1, then we have an entangled state. Now, how do we see that this is an entangled state in the lab? How is it manifested in the lab? So we take our crystal and we take a single photon detector, fiber coupled in our case, and we scan the position of the fiber end, and we register the number of photons that we collect at each point. Okay, this is what we call the single photon counts. And because, as we said, we tweak the crystal parameters to have a wide range of angles emitted from the crystal, we get a wide distribution of the single photon counts. But how do we see that they are emitted in pairs and that these pairs are correlated? We take another single photon detector. Okay, and now we look for what we call the coincidence event. We register all the cases where two photons get to the two detectors simultaneously. We fix the position of one detector, we scan the position on the other, and we look for the events where both detectors fire simultaneously. This is what we call the coincidence count rate. And now we see that we get a very localized map. Again, this is because of momentum conservation. There's only one position of the scanning detector where we'll see co-registration of events on the two detectors. So we get a localized map. This is a hallmark of high-dimensional entanglement, where we have a very broad distribution of single photon counts and a localized coincidence count rate. Now, this is still not a proof of entanglement. In order to prove that these photons are in entangled state, we need to repeat this measurement also in the near field. I should have mentioned all these measurements were taken in the far field of the crystal. If we repeat this measurement and see also a localized coincidence count rate in the near field and a broad distribution in the near field, then one can prove that this is indeed entangled state. Okay, so this is how we generate spatially entangled photons. And now we want to ask the question of what happens when these photons pass through a scattering layer, like, for example, atmospheric turbulence, and what will happen to these correlations. So we add a thin diffuser right after the nonlinear crystal, and we repeat the measurement. Again, we have two detectors. One is fixed, the other is scanning. Now, if you just look at the single photon counts of the scanning detector, we don't see anything special. Okay, we again see a broad homogeneous distribution of the photons, and this is because we emit the diffuser in a wide range of angles, and because it's a single photons, there's no well-defined phase between the different angles, so we get a broad distribution of the single photon counts. But if we look at the coincidence count rate, now we do see a structure. We see actually speckle, or what people defined about a decade ago as a two-photon speckle. This is a speckle that we see in the coincidence rate, right? In the cases where we have both two photons detected simultaneously on the two detectors. And the reason now we see speckle and specifically an interference effect, for example, whenever we see dark pixels, we get destructive interference. And the reason for this is that once a photon is detected, say, in this detector, the twin photon collapses to a superposition of states, and this superposition is coherent and can show constructive and destructive interference. Now, when you think about it, this, for example, if you look at this pixel, which has a destructive interference, it's an interesting case where both detectors see photons all the time. Okay, they see photons, both of them click, but they never click simultaneously because the superposition that the photon has collapsed into had a destructive interference on this pixel. So there's photons on both detectors, but they never arrive simultaneously. This is the two-photon speckle that was first discovered about a decade ago, as I mentioned. And now I want to ask the question whether we can do adaptive shaping for these photons so that after the scattering layer, they will get back the nice localized two-photon coincidence rate instead of the two-photon speckle. So this is the question we're asking: can we do adaptive shaping to these entangled photons and compensate for scattering? And let me just briefly mention what people are doing in wavefront shaping of classical light. So we know that with using spatial light modulators, we can find a wavefront that we need to illuminate a thin scattering layer so that after the diffuser, the scattering layer, light will be focused or nearly focused to a spot. There's many different ways to do this. You can pre-measure the transmission matrix of the scattering layer, or you can do it adaptively. You choose a pixel and you look for the SLM, and you choose a pixel you want to maximize the intensity on, and you use some optimization algorithm using the feedback from the camera to search for the wavefront that will focus the light after the scattering layer. And this was first realized in this seminal paper by Mosk and Velikup, and since been applied to many different scenarios and for classical light. Now, in recent years, people have been trying to use a similar approach also for quantum light, for single and entangled photon, and there's a lot of work on adaptive optics and wavefront shaping on single and entangled photons. And in most of these works, what's usually been done is that you put a spatial light modulator after the entangled photons or the single photons were generated and before the scattering layer. And you look for the compensation, the correction you need to apply using the SLM in order to correct for these two photon speckles. Now, this works. People have shown that this works, but there are a few caveats, and two of the main ones are that essentially putting a spatial light modulator, even if its efficiency is very high, essentially it's a lossy process, especially if you want to control both amplitude and phase. And the thing is with entangled photons is that you're quadratic in the loss, because if you lost one photon, you lost the pair. You can't do anything with just one out of the two pairs. So you want to minimize, and to start with, the quantum signal is very low. So we want to minimize as much as possible the loss on the SLM. And so the loss of the entangled photon. So adding another SLM on them is not ideal. Another thing is that, as we mentioned, you need some kind of feedback in order to compensate, to find the correction you need for the entangled photons. And since we're using very weak signals, quantum lights is manifested with very weak detection signals, then what people usually do is add an auxiliary bright laser, do the compensation on the laser, and if the laser has the same polarization, the same wavelength, and the same shape as the entangled photons, then you can quickly switch between the auxiliary beam and the entangled photons and hope that the correction still holds. The correction you find still holds also for the entangled photons. Now, we want to find a different way to do this, and what we propose to do is to take the spatial light modulator and use it to structure the pump beam. So we move the SLM and use it to structure the pump beam that stimulates the generation of the signal in either photon in the nonlinear crystal. This would be ideal because the power of the pump laser is for free, right? You could just pay a little bit more, buy a more expensive laser, and get more photons for the pump. And also, since it's one photon of the pump that is converted to a pair of photons, if we have a loss on the pump, we are linear in the loss of the pump. So this solves the loss issue when you introduce an SLM. The problem is then what can we use for the feedback? Because if we control the photons, the high frequency photons, the blue photons in our case, what kind of feedback can you use? Because essentially we want to compensate for the red photons, for the entangled photons. So what we propose to do and demonstrate is to put a dichroic mirror, let the red photons, entangled photons, pass to their target, and but collect the pump photon, let it also pass through the scattering layer, and do the wavefront optimization algorithm solely on the pump photon. So this is a classical wavefront shaping optimization we apply on the pump beam, just like Mosk and Velikov. Okay, so the pump is controlled by the SLM. It scatters through the scattering layer, picked up by the dichroic mirror. We choose a pixel on the camera we want to focus, and we apply the adaptive optics or the wavefront shaping correction algorithm. And simultaneously, at the same time, the entangled photons, the red arrows, as they were manifested here, pass through the single photon detectors. Now, this is nice. We know we could do very efficiently the optimization on the pump photons, and the pump contains, as we mentioned, lots of photons. So this can be done very quickly and efficiently. But the question that one might ask is, why would compensation of the blue photons help to compensate for the scattering of the red photons? Because there are totally different wavelengths, right? We have blue photons for the pump at 400 nanometers, and the entangled photons are at 800 nanometers. And we know from classical light that when we have speckle, when we have scattering of coherent light, different wavelengths will generate different speckle patterns, right? Here's an example of a white light laser passing through a scattering layer, and you see that the blue and red photons scatter in a very different way. So why would optimization of the blue pump photons help with optimizing the scattering of the entangled photons? But one must remember that we are dealing here with two-photon speckle. We try to compensate for two-photon speckle for the quantum light. And there, what our signal, what we measure is correlations. It's those coincidence events between pairs of photons. We're not trying to compensate for their intensity, for the mean photon number, for the single photon counts, as we called them earlier. And once we try to compensate for correlations, things behave differently. And it turns out, and this is quite known in quantum optics, that when you look at the correlations between two entangled photons at some wavelength lambda, they act and behave as a single photon at half the wavelength. And this is known for dispersion and for polarization rotation, and what we claim here that it's also true for scattering. So let's see how it looks indeed in the lab. First, before applying the compensation, we check that indeed two-photon speckle at 800 nanometers look at like the pump speckle at 400 nanometer. So what you see here is an image we took of the pump beam after the scattering layer, and you see the speckle of the pump. And now if you compare it visually with the two-photon speckle, you see, okay, so these are the speckles we get at the coincidence rate after the pairs of photons propagated through the scattering layer, and you see that we get pretty much similar features. Okay, we have a bright spot here and here for the pump, and also for the two-photon speckle. Of course, the two-photon speckle is much more noisy. It's noisy because we have here just each pixel here contains something like a few tens of counts per second. Okay, so we suffer for the Poissonian noise. This is why this image is much noisier, and the pump is nice and sharp because it has 10 to the 13, 10 to the 14 photons per second hitting the camera, each pixel of the camera. Another difference is that you see that there's a correspondence between the two patterns, but they're scaled one relative to the other. So you see the window here, the field of view here is 2 millimeters, here is 1 millimeter, and this is because the correlations of the pair look as if it's one photon scattering at half the wavelength, but the light still remembers, right? The entangled photon still remembers, so to say, that they're red, okay, that their wavelength is 2 times larger, so their diffraction is 2 times larger as well. So we get the same pattern, but scaled by the factor of 2. But we don't care so much about this scaling as if all we want to do, if our purpose is to focus the pump speckle and the two-photon speckle, the scaling doesn't affect us. So now we can apply the classical optimization, wavefront optimization for the pump speckle, and see whether the two-photon speckle will focus simultaneously. And indeed, this is what we see when we apply the optimization process. So over here on the left, you see the two-photon speckle before optimization. In the instant on the right, you see how the pump beam looks after we apply the wavefront optimization algorithm. And you can see in the larger panel that the two-photon speckle, or it's no longer a speckle, the two-photon coincidence map became localized simultaneously with the pump beam. So we applied optimization on the pump, and we get optimization on the pump beam. Optimization on the pump beam simultaneously localized the two-photon coincidence rate of the entangled photons. Next, we moved the diffuser as we applied optimization. And again, we optimize the pump beam. So this is the signal you can see in red. And as we optimize, the signal of the pump increases. And then until it gets to a saturation where, because of the diffuser moves and we keep compensating. Once we turn off the optimization, the signal of the pump beam decays. And what you see here is that we measure simultaneously the two-photon coincidence rate, and it nicely follows the signal of the pump beam. So we compensate it as we optimize the pump beam, and once we turn off the optimization, both of them decay. Of course, the two-photon signal is much noisier because, again, the Poissonian noise. Now, as you can see probably here, the time scales here are very slow because we wanted to be able to collect enough signal for the coincidence rate to show that it follows the pumping. But we can go faster if we probe the coincidence rate at lower rates. And then you can see that our optimization currently works for timescales of a few minutes. Okay, so the diffuser moves, it takes about 1 minute for the diffuser to move in order to completely change the speckle pattern that we want to optimize. This is still, of course, very slow if we want to apply this to real life scenarios, but we're currently limited by the slow electronics and SLM we're using, and of course that using faster electronics and deformable mirror devices we could probably or for sure go much faster. It's a thin diffuser. Now you might ask yourself how thin the diffuser should be in order for this to work. And we did some analysis to show that, in fact, what you want to do is to have in order for this method to work is that the pair of photons needs to pass through the same coherence area of your diffuser, of your scattering layer, where the coherence area is defined by the area for which the phase accumulated by the light passing through it is the same. We denote it here by small d. So both photons and the entangled photons and the pump photons should pass through the same coherence area. Now, the entire beam can pass through multiple coherence areas. This is why we get speckled, because remember, we're in a superposition of pairs, and this superposition means that we have a superposition of pairs hitting different areas of the diffuser, but as long as the two pairs propagate through the same coherence area, and here we model a volume diffuser by two diffuser at some spacing z between them, which would be like the thickness of the diffuser, and one can show that as long as this thickness, effective thickness of the diffuser is smaller than d squared, d coherence area squared over the wavelength, then the method should work. And so it all depends how thin the scattering there should be, depends on its coherence area. And a nice application is for atmosphere, where the coherence area could be quite large, a few centimeters or a few tens of centimeters. And we checked that using numerical simulations, and we showed that even the method can work even for lengths that are up to a few tens or even 100 of kilometers, depending on the strength of the turbulence. And what we show here is in the dots is how long the link, or how long the photons can propagate before the quantum signal is degraded, and the dots are before we applied our compensation method, and the solid curves are after applying the compensation, and you can see that we can get up to 2 orders of magnitude increase in the link distance. Just a couple of words on the simulation. So what we do in the simulation, and this is following Kolmogorov phase mask, and there are several good papers and reviews on how to simulate propagation of light through the atmosphere. Basically, you could emulate the effect of turbulence using phase masks, where you can compute for different strengths of turbulence, different phase masks, and then one can show that the speckles you get after a coherent beam passes through these phase masks, and the speckles and their statistics match quite well. It's both analytically and experimentally the speckles you expect to get from propagation of light through the atmosphere. So now, using the same idea of Kolmogorov phase mask, we check this in the lab for phase correcting. For compensating scattering of photons that are scattered by Kolmogorov phase masks. And the way we do this, we just replace the scattering layer we had before with another SLM, an SLM that is used just to emulate atmospheric turbulence. So we have two SLMs, one for emulating the turbulence and the other, as before, for shaping the pump beam. Of course, we don't use, in order to find the correction phase mask, we apply the feedback algorithm we had before. We don't use the information we know on the scattering layer, because we computed first the phase mask using Kolmogorov theory to emulate the turbulence. So we apply the optimization for the Kolmogorov, for compensating the Kolmogorov phase screens, and we see that it works quite well, and as good as the compensation we had for the thin diffuser. So this is how the two-photon coincidence rate before we apply the turbulence. This is after we apply the turbulence, and then we apply the turbulence plus the wavefront optimization, and we localize the two-photon map back again thanks to the corrections. Okay, let me, I'm very close to saturate my time limit here, so let me end by just mentioning that all the results I showed you so far were for what we call degenerate entangled photons, which means they have the same wavelength. So that what we showed again is that the pumped two-photon speckle and the degenerate photons show similar two-photon speckle, and you can compensate for them simultaneously. What we've also showed is that this also works when the signal in either photons have different wavelength. Okay, in the non-degenerate case, again, you can see that we before optimization it shows similar features to the pump speckle, and once we focus the pump beam, the coincident rate focus simultaneously. So the method also works for non-degenerate photon pairs. It also works for non-collinear pairs. So the signal in either photons don't have to propagate at the same direction as the pump beam. They can also, if you tweak the phase matching conditions to be non-collinear, they can propagate at different angles. So in the far field without a scattering layer, then you see a ring, and the correlations mean that the photon that is detected here, its twin photon will be on the other side of the ring. Now we apply a scattering layer. Now remember, the scattering layer is in the near field of the crystal, not in the far field. So it's in the far field that they go we see them at different positions, but in the near field they're still close by, so they do pass through the same area of the scattering layer. So this is after they pass through the scattering layer, and when we apply the compensation or optimization, we see that the coincident rate becomes localized again. So it works for non-degenerate, non-collinear. It's very, very general. Okay, so I think that at this point I should conclude, and my main message was that by applying pump shaping, by shaping the pump, we can adaptively change the structure of the entangled photons, and by this compensate for scattering, dynamic scattering of entangled photons. And we like a lot this pump shaping approach because it doesn't introduce loss to the system, and because we have a strong signal of the pump beam, it can allow real-time compensation. Of course, there's no free lunch, and there's also a price we have to pay for applying the pump shaping. And one of this is, as I mentioned, it works for relatively thin samples, and how thin depends on the size, the volume of the coherence area. We're now trying to apply and see how we can extend this to also thicker samples, and in analogy to what people do in adaptive optics for compensating for atmospheric turbulence of classical light. This would mean to go beyond the isoplanatic patch. This is one line of research. Another price we have to pay for this method is that it works very well, as I showed you, when we send both photons, both pairs, through the same scattering layer. However, this quite limits the application work, because in many quantum communication protocols, the sender keeps one photon on his side and transmit only one photon to the other side. But there are algorithms where both photons are sent, and for those algorithms, for those quantum communication protocols, we believe our method of pump shaping could be applied immediately. And we're also working on to see how we can adapt this pump shaping method for protocols that require keeping one photon at the transmitter side and sending only one photon to the other side. Okay, and let me end here by thanking my group, and especially Oad Lieb and Ronen Shekel, who were in charge on the results and the experiments I've showed you so far. And I'll thank the funding agency, and I also thank you for listening, and I'll be happy to answer questions in the Q&A session. So bye for now.